Slide 1. Atoms, Molecules, and Seawater Chemistry, Topic 04A, Part 1, Temperature, Heat, and the Motions of Atoms and Molecules. Slide 2. Breaking bonds. Bond is the word we use to describe the electrical attraction between atoms or molecules that holds the atoms and molecules together, that keeps them from moving apart, from moving away from one another. The greater the distance between a pair of atoms or molecules, the weaker the electrical attraction between them. In other words, the greater the distance between the bonded atoms or molecules, the weaker the bond. If the atoms or molecules move fast enough, their speed can overcome the electrical attraction, they can get far enough apart that the electrical attraction becomes tiny, and the atoms or molecules will fly apart. In other words, if atoms or molecules move too fast, the bonds holding them together will break. The same thing is true of rockets that blast off into outer space. A rocket has to move very fast to overcome the gravitational attraction of the Earth. The speed needed to leave the Earth and go off into space is called the escape velocity. If atoms or molecules move fast enough, they too can escape one another. When liquid water becomes a gas, water vapor, the water molecules fly apart and into the atmosphere. In other words, the bonds holding the water molecules together must break for the water to evaporate. If I asked you to make water transform from a liquid to a gas, you would probably put a pot of water on a hot stove burner. This observation, that water transforms when heated enough, suggests that temperature must be related to the speed of the atoms and molecules. The higher the temperature of the substance, the faster its atoms and molecules are moving. Eventually, they move fast enough for the bonds to break and thus produce the change from liquid to gas. Slide 3. Solids, liquids, and gases. A solid, like ice or salt, has slowly moving atoms and molecules with strong bonds. The atoms and molecules of a solid are constantly moving, but they are wiggling in place, they vibrate, oscillate, but don't leave their spot, like a child fidgeting in their stroller or car seat. The atoms and molecules of a solid do not leave their spot, because they are strongly bonded to neighboring atoms and molecules. The strong bonds of their neighbors hold them in place. A solid has a fixed, unchanging size and shape because all the atoms and molecules of the solid are firmly attached to their neighbors. In gases like water vapor or oxygen, on the other hand, there are no bonds between the gas atoms or molecules, because the atoms and molecules are moving too fast. When the gas atoms or molecules bump into one another, the electrical attraction they feel for one another increases, but it is not strong enough to hold them together. Thus, a gas has no fixed size or shape, it will expand to fill whatever space is available since the atoms and molecules of the gas do not hold onto one another, they do not keep one another from flying off. A liquid like ordinary water is somewhere in between a solid and a gas. The water molecules are often moving fast enough to break their bonds with their neighboring water molecules. However, they immediately form new bonds with their new neighbors. Thus, liquids can flow, change their shape, because bonds are easily broken, but the molecules of the liquid do not fly apart because they are always bonded to some of their neighboring water molecules. The bonds between the water molecules are strong enough to hold the molecules together in a group, but not strong enough to keep them in place, to keep them from moving around. The bonds formed by atoms and molecules of a liquid are not too strong and not too weak, and the speed of the molecules is not too fast and not too slow. Note, we call solids, liquids, and gases different phases or states of matter. There is another state of matter called a plasma in which protons and electrons no longer stay together and fly apart. Slide 4. Latent heat. Latent heat is the amount of heat that must be added to make molecules break their bonds or the amount of heat that must be removed to allow molecules to form new bonds. The added heat makes the molecules move faster. The farther apart their wiggling carries them, the weaker the electrical attraction holding them together becomes and the easier it is for them to fly apart. Removing heat slows the molecules down. If they are going slow enough when they come close together, the electrical attraction will increase enough to hold them together. When sunlight makes ocean water evaporate, we say that the water gained latent heat, and when water cools and condenses in the atmosphere, we say that the water lost latent heat to the neighboring air molecules. Cooling equals losing heat. Since latent heat is heat that breaks bonds or allows them to form, latent heat is the amount of heat that must be added or removed to make a substance transform from one phase, solid, liquid, gas, to another phase. Therefore, latent heat is being added when something evaporates, transforms from a liquid into a gas, or melts, transforms from a solid into a liquid. Latent heat is being lost when something condenses, transforms from a gas into a liquid, or freezes, transforms from a liquid into a solid. When a substance transforms from one phase, solid, liquid, or gas, to another phase, then you know it must have gained or lost heat. Students should be able to identify whether the substance gained or lost heat and whether bonds formed or were broken, and be able to propose a reasonable hypothesis about where the heat came from. For example, if the sun heats ocean water and the water evaporates, the water gained heat, causing water molecules to speed up and break their bonds with their neighboring water molecules and become a gas. Later on in the atmosphere, these water molecules encounter the cooler air molecules, oxygen and nitrogen molecules. When the hot water molecules collide with the cooler air molecules, heat goes from the warmer water molecules to the cooler air molecules. Hot molecules move faster than cold molecules, so when the water molecules give some of their heat to the air molecules, the water molecules slow down. The water molecules now are moving slow enough that when they get close to one another, their mutual electrical attraction is able to hold them together. In other words, once the water molecules slow down, cool down, the water molecules can bond with one another when they meet, to become part of a liquid, a drop of rain that falls back into the ocean. Slide 5. If you throw a ball upwards, it slows down due to the gravitational attraction of the Earth pulling it downwards. This happens to a rocket trying to escape the Earth. The Earth's gravitational pull slows the rocket down. In other words, the rocket would be going a lot faster if it didn't constantly have the Earth's gravitational pull working against it. The same thing is true of atoms and molecules when they break their bonds. The energy, the heat added, does not all contribute to the speed of the atoms and molecules, which is related to their temperature, how hot or cold the atoms and molecules are. Some of the heat gained by the molecules must be used to overcome the electrical attraction, to break the bonds. This energy does not contribute to the temperature of the atoms or molecules. In other words, when heat is added to a substance, some of the heat is used to break the bonds, to cause the transformation from solid to liquid or from liquid to gas, and some of the heat increases the temperature of the substance. Let us look at a concrete example. Suppose that some water gains 100 joules of heat. 10 joules of heat might cause some of the water to transform into water vapor, a gas, while 90 joules of heat might cause the temperature of the water to increase. As you can see from this example, not all of the heat gained by a substance causes its temperature to go up. This is the key point that I would like you to understand. The boiling point of a substance is the temperature that it cannot go above and remain a liquid. It must transform into a gas for its temperature to go above its boiling point. The melting point of a substance is the temperature that it cannot go above and remain a solid. It must transform into liquid for its temperature to go above its melting point. We learned a moment ago that the heat that causes transformation is called latent heat. As the temperature of a substance increases and a solid gets closer to its melting point or a liquid gets closer to its boiling point, more of the heat gained is latent heat and less heat causes the temperature to change. In fact, adding heat will not increase the temperature of a substance when it is at its melting point or its boiling point. All the heat added is latent heat that is breaking the bonds holding the atoms and molecules of the substance together instead of making the atoms and molecules move faster. This means that a pot filled with melting ice water will remain at 0 C while the ice is melting, even if the stove burner is on high. Similarly, the temperature of boiling water on a stove remains at 100 degrees Celsius even though more and more heat is being applied. Technically, 0 degrees Celsius and 100 degrees Celsius are the freezing and boiling points, respectively, of fresh water at 1 atmosphere of pressure. Water has an unusually high latent heat of evaporation and an unusually high latent heat of melting. Compared to other substances, water has extremely large latent heats of melting and evaporation, because of the unusually strong bonds, hydrogen bonds, between the water molecules. The strong bonds keep the molecules together, making it harder for ice to melt, turn into liquid water, or liquid water to evaporate, turn into gas. More heat must be added to break these bonds. At temperatures where most small molecules that are similar to water, oxygen, carbon dioxide, nitrogen, and so on, fly apart and are gases, water molecules form solid ice or liquid water, because their stronger bonds hold them together. Slide 6. Thermal expansion and contraction. During the first week of the semester we learned that if you heat a substance like water, it will expand, get bigger, take up more space, and if you cool a substance, it will contract, get smaller, take up less space. This is called thermal expansion and contraction. We now have enough knowledge of atoms and molecules to understand why thermal expansion and contraction occur. When atoms or molecules of a substance are heated, they move faster. They bump into their neighbors more strongly, and this jostling causes them to push away from one another, they spread out a bit more. The atoms or molecules spreading out not only increases the size of the object, but it also lowers the density of the substance. Similarly, cooling an object, removing heat, causes its atoms or molecules to move slower, so they don't push away from one another as strongly when they collide, and their electrical attraction, bonds, bring them closer together. Thus, the object's size decreases, and its density increases. Note, the molecules themselves do not expand, get bigger, or contract, get smaller. The molecules get farther apart or closer together, and this causes the substance or object they are part of to get bigger or smaller. Slide 7. The freezing points of water and seawater. There is one major exception to the rule that heating things make them expand and cooling things makes them contract. At the freezing point of water, and only at the freezing point, cooling water decreases the water's density. Unlike most other substances, the solid form of water, ice, has a lower density than the liquid form, liquid water, so it floats. Ice has a lower density than liquid water, because its molecules are more spread out in ice than when they are liquid owing to the shape of water molecules. Water molecules have a triangular or bent shape and can only bond in certain directions, because one side of the molecule is electrically positive and the other side is electrically negative. In a liquid, water molecules do not have to bond in these specific directions on all sides, they are constantly shifting and sliding past one another. If you try to fit water molecules together in these directions, though, you find that you have a lot of empty space, since each water molecule bends through an angle of about 105 degrees, 6 water molecules form a big circle with a hole in the middle. Thus, water crystals tend to have 6-sided symmetries, as you can see in pictures of snowflakes. Salt atoms cannot fit into the final crystal structure of ice well, because of mismatches in size and bonding directions. A salt atom is either positive or negative all the way around, it does not have a positive side and a negative side like water. Slide 8. Thus, salt in seawater gets in the way of the freezing process, making it harder for the water to freeze into ice until it is pushed out of the way. This lowers the freezing point of seawater by about 2 degrees Celsius or 3.5 degrees Fahrenheit, and also means that sea ice contains less salt than seawater. This was very useful to early Arctic explorers who learned to drink melted sea ice. Oceanographers say that the salt is rejected by the sea ice, and therefore the rejected salt stays in the unfrozen ocean water, making it more salty, and thus harder to freeze. This happens again and again during the winter. Eventually the surface water becomes both cold and salty enough to sink down deep into the ocean instead of freezing into ice. Slide 9. Heat capacity. Think about a hot afternoon at the beach. Both the sand and the water get the same amount of heat from the sun, but which is warmer, the sand or the water? Clearly, the sand is much warmer than the water. This means water has a high heat capacity, meaning that it holds more heat than another substance with the same temperature. Think of heat capacity as a kind of thermal inertia. An object with a large inertia, mass or weight, is much harder to move than an object with a small inertia. In the same way, it is hard to change the temperature of a substance, like water, with a high heat capacity. So water does not get as hot or as cold as the land, it takes more heat to raise its temperature, and it must lose more heat to lower its temperature. So, why do we call this property heat capacity if the hotter object, sand, has the lower heat capacity? Think about nighttime when the situation is reversed. The ocean, high heat capacity, is warmer than the land, because it resists cooling down. This makes sense, right? So, however you define this property, one situation or the other, day or night, is going to be confusing, seem backwards. Slide 10. Why is this the best way to define heat capacity? Consider your experiences biting into a hot piece of pizza. The crust may be warm, but the watery sauce and cheese burn the roof of your mouth, because they are much hotter. All three, bread, sauce, and cheese, were warmed up to the same temperature of 400 degrees Fahrenheit or more in the oven, but the watery sauce and cheese have a higher heat capacity, so they had to absorb more heat to reach this temperature. All three, bread, sauce, and cheese, lose heat as the pizza cools when it is pulled out of the oven, but the crust cools down faster, because it has less heat in it to begin with due to the crust's low heat capacity. The sauce and cheese have a lot more heat to give up, so it takes longer for them to cool down, and they remain warm enough to burn you. The heat capacity of a substance is the amount of heat that you need to add to change the temperature of a unit mass by 1 degree. Technically, I am describing the specific heat capacity. I just call it heat capacity to make it shorter and easier to write and say. Since water has a high heat capacity, you need to add a lot of heat to water to get its temperature to go up by a small amount, like 1 degree. But this also means that you need to remove a lot of heat from water to get its temperature to go down by a small amount. Why do water molecules have an unusually high heat capacity? Well, that is difficult to explain in a simple way. As usual, it is related to water's unusually strong bonds, but it also has to do with how temperature is related to heat. As we know, heat makes atoms and molecules move faster, but temperature is mainly related to the wiggling or movement of the entire molecule. However, there are other motions that the heat can cause: rotation, spinning, vibrations within the molecule, and so on. Heat that goes into these motions does not contribute to temperature. So, the key to water's higher heat capacity is that the atoms within water molecules have more motion options than the atoms in other molecules. Slide 11. The climate along the coast is much nicer than the climate farther inland, away from the coast, because of the high heat capacity of ocean water. The coastal climate is more moderate, not as hot during the summer and not as cold during the winter. During the summer, the ocean does not warm up as much as the land. Breezes cooled by ocean water blow to the coast sometimes, helping to keep the coast cooler during the summer. During the winter, the ocean does not get as cold as the land. Breezes from the ocean are affected by the temperature of the ocean water, so they are not as cold as breezes from farther inland. I should note that heat capacity is not the only reason that sand is warmer than ocean water on a hot afternoon. As we learned in Unit 2A, the ocean environment, other factors can be important too, like how deep sunlight penetrates, and mixing caused by waves and other factors. Even latent heat plays a role, since it is the warmest water molecules that evaporate from ocean, leaving the cooler molecules behind in the ocean. Slide 12. Water molecules have just the right bonding strength, not too strong and not too weak, so that they can remain a liquid over a large range of temperatures and pressures. Think of the story of Goldilocks and the Three Bears. Papa Bear's porridge is too hot, Mama Bear's porridge is too cold, and Baby Bear's porridge is just right. The bonding strength of water molecules is like Baby Bear's porridge, just right. The fact that water remains a liquid over a wide range of temperatures and pressures is crucial for life. Living things cannot exist without liquids. The molecules of a gas do not stay together, but fly apart, so you cannot construct a body with a gas. Solids, on the other hand, do not change, something living organisms must do all the time. This is why the human body is mostly made of water. Slide 13. There is another reason that it is a good thing that water molecules do not hold onto one another too strongly. Most of our fresh water evaporated from the ocean not so long ago. The bonds are strong enough to keep most water in the form of a liquid here at the surface of the earth, but not so strong that some water cannot evaporate and provide the rain that is our source of fresh water. Slide 14. Diffusion. As we see during the lab, atoms and molecules never stop moving. Add a drop of dye to a container of water and the dye will naturally spread out on its own without any stirring. The water molecules bond with the dye molecules, and carry the dye molecules with them as they move around the tank. Eventually the tank is one uniform color, because the water molecules and dye are equally likely to be found everywhere since they are moving around and bumping into one another at random. This random motion of liquid and gas molecules leads to substances spreading out and mixing over time. As a result, substances that are concentrated in one place spread out until they are evenly distributed everywhere, until the concentration is the same everywhere. We say the substances are diffusing, that they have undergone diffusion. Diffusion happens to sugar in your beverages, and salt in your soup. Over time, the sugar spreads out even without stirring, and it will never unmix and fall to the bottom. In other words, it never becomes concentrated in one place again. Stirring does help sugar spread out, of course, by helping the sugar molecules move around quickly and meet more unattached, unbonded, water molecules. Diffusion results in a fluid that is the same everywhere. Over time, randomly moving atoms and molecules tend to move from the place where they are most concentrated, where there are more of them, to where they are less concentrated. In other words, if there is more of something in one place, like salt atoms, and they are randomly moving around in a container, then over time eventually the salt atoms will be spread equally throughout the container. There will no longer be one spot with more salt, with a higher concentration of salt. Diffusion is very important for life in the ocean. Many microscopic organisms get substances that they need, nutrients, carbon dioxide, oxygen, and so on, when the random motion of molecules brings dissolved substances that they need to their bodies. Similarly, wastes, like oxygen or carbon dioxide, just drift out of their bodies naturally. Like other molecules, randomly moving water molecules tend to move from the place where they are most concentrated to where they are less concentrated. In other words, their movement tends to even out differences as more time passes. If ocean water is too salty for an organism, saltier than the cells of its body, water molecules leave its body, moving outside and reducing the ocean's salinity. It might be helpful to think of the water molecules moving out of the body to bond with the excess salt atoms. The organism then suffers from dehydration, lack of water. This is why freshwater fish cannot live in the ocean. A freshwater fish dies of thirst in the ocean. Similarly, if the ocean is too fresh for an organism, the ocean has a lower salinity than the cells of its body, extra water molecules will enter their body, and cause the organism and its cells to bloat. The excess water can interfere with the regular operation of the cell and even inflate it so much that it bursts. Something like this can happen in our own bodies. If you drink too much seawater, water from your body's tissues will move into your stomach, where the salt is, and then be lost from your body when you excrete, pee. As a result, you become dehydrated, lose too much water. Our bodies cannot be so open to our environment as those of ocean organisms. If our body's cells were like those of most ocean animals, we would quickly lose most of our water to the surrounded by air. Our cells are better at keeping the stuff inside us in and the stuff outside us out. Slide 15. Atoms and molecules never stop moving. As we see during the seawater chemistry lab, even in seemingly still water, the water molecules are moving. Your instructor dropped dye into still water at the beginning of class, and the dye immediately started to spread, and continued to do so. The dye kept spreading and spreading because the water molecules themselves continued to move. They do not get slower and slower over time. They never stop, even in water that looks calm and motionless. Unlike ordinary objects, atoms and molecules never stop moving, because there is no friction on the atomic level. Friction results when two objects rub against one another, causing their atoms and molecules to bump into one another. This causes the atoms and molecules to move faster. In other words, it generates heat and warms them up, but the objects themselves slow down and are brought to a stop to compensate. The organized energy of all the atoms and molecules moving forward together inside their object, kinetic energy of the object, is transformed into the disordered energy of all the atoms and molecules wiggling randomly, heat in the object and its environment. No motion, no energy is lost from the universe, it is merely transformed from one kind of motion to another kind of motion, one kind of energy to another kind of energy. Physicists call this the conservation of energy. Energy transforms from one kind of energy to another kind of energy but does not disappear from the universe. By the way, you know from your own experience that friction produces heat. Just rub your hands together. Slide 16. Why heat flows from hot objects to cold objects. We all know that heat flows from the hotter object to the cooler object. If you think about your experiences with collisions, you can understand why. When two objects collide, typically the faster moving object gives its energy to the slower moving object, causing the slower moving object to speed up. The faster moving object loses energy, so it slows down. Think of a car getting rear-ended. The car behind will slow down, and the car in front will speed up. Similarly, atoms and molecules are constantly bumping into one another. When warmer, faster-moving molecules hit cooler, slower-moving molecules, the cooler molecules gain energy and speed up, get warmer, while the warmer molecules lose energy and slow down, get cooler. The warmer molecules in a substance tend to give the cooler molecules their energy via collisions until all the molecules have about the same speed, in other words, until they have reached the same temperature. Why heat flows from hot objects to cold objects. A few more comments. The previous discussion oversimplifies molecular collisions. In particular, the objects are assumed to have similar masses. Also, both energy and momentum, translational and rotational, are exchanged in collisions, and in solids and liquids potential energy must be considered as well. Moreover, there is a distribution of speeds, because less likely collisions do occur in which energy is transferred from cooler molecules to warmer ones. These kinds of collisions become more common when all the molecules have similar speeds. Slide 17. Answering questions using the atomic theory of matter. This section of the class is often one of the more challenging ones for students. The most common mistake on assessments is that students discuss what happens at our scale rather than what happens at the microscopic level of atoms and molecules. So, when answering questions using the atomic theory of matter, make sure that you discuss the behavior of the atoms and/or molecules. In other words, if your answer discusses water evaporating or salt dissolving, then you have not answered the question. Instead, you should discuss the speed of the water molecules and salt atoms, as well as the bonds between the water molecules and salt atoms. To describe atoms and molecules' behavior, discuss their motion and bonding. Electrical attraction: are new bonds forming? Are bonds breaking? Getting stronger or weaker? Why? Are the molecules moving fast or slow? Are they wiggling in place or traveling, flying from place to place? How do collisions with other molecules affect them?